Hello, everyone, and thanks for joining this webinar on deep dive and best practices for Amazon Redshift. Over the next 1 hour, we will take this opportunity to understand Amazon Redshift in a little bit more detail and look at some of the best practices that you can apply to make sure you are optimally utilizing Amazon Redshift. My name is Raghuraman Balachandran. I work as a big data solutions architect for Amazon Internet Services in India. Here's a quick look at the agenda that we'll go for today. We will start with a brief overview of what Amazon Redshift is for those of you who are new to Amazon Redshift. And then we will jump and dive deep into some of the concepts and the table design. We will then move on to things like data storage, how do you ingest data, how do you do ELT, and so on and so forth. Later, we will talk a little bit around workload management, which is one of the key elements of Amazon Redshift, and some of the newer ways through which you can automate workload management using things like query monitoring rules. Towards the end, we will talk about node types and cluster sizing and so on and so forth. And I will also leave you with some additional resources that you can refer for your further reading. At any point in during the webinar, if you have any questions, please do drop the questions through the questions window on the webinar panel. We have solution architects who are standing by on the webinar, and we will do live Q&A where they would respond to your questions through the questions window. So feel free and go and drop your questions on the questions panel. Yeah. Okay, so with that, let's get started. Let's quickly understand at a high level what Amazon Redshift is, and then we'll start diving deep into those topics, right? So for those of you who are already using Amazon Redshift, you would be well aware that it's a relational data warehouse built on MPP architecture, massively parallel processing architecture. It's a shared netting architecture where you have multiple nodes in the cluster, and you can utilize all the nodes for your processing requirements, right? So when you go to Amazon Redshift console and say that you want a data warehousing cluster, you go and specify a few properties like how many nodes you want and so on and so forth, and go ahead and spin up the cluster. So behind the scenes, what happens is when you say I want so many nodes in the cluster, you're essentially referring to what is called as compute nodes. These compute nodes are the ones which are holding your data, and they are the ones which are running your queries when you submit the queries to the cluster. You as a customer, you can decide how many number of compute nodes you want, and there are different types of compute nodes. We will talk about it towards the end of the webinar. But once you provision the cluster, we automatically throw a leader node. The responsibility of the leader node is to expose a DNS endpoint through which it can receive SQL queries. So you can use any popular SQL client or BI tool which supports JDBC or EBC that can directly connect to the DNS endpoint that the leader node exposes and submit queries to the cluster. Now, once the leader node receives the query, it prepares the query execution plan, compiles the runtime compile code, sends the code down to the compute nodes. The compute node work on their own data set based on the code that was given by the leader node. And then they submit partial results back to the leader node. The leader node does the final aggregation and sends back the result to the SQL client, right? In addition to the compute nodes, every Redshift cluster also has access to what is called as Amazon Redshift Spectrum. So Spectrum is a feature of Amazon Redshift through which your Redshift cluster can directly talk to Amazon S3, right? You can hold your data on Amazon S3 and you can submit a query which can directly run against that data set available on Amazon S3. So that's the high-level architecture of Redshift, right? Now let's dive a little deep onto some of the concepts, starting with the first one, which is one of the fundamental differences of Redshift, right? So Redshift, like I said earlier, it is a relational database, but it's a columnar database, right? So it uses a columnar architecture when it stores the data in the underlying disk. The key goal by following a columnar architecture is essentially to reduce the IO operations for your queries. right? When you're storing the data physically on a columnar format, when you're submitting analytical queries, which typically scan only a subset of the columns of your table, through a columnar architecture, you can effectively read only the columns that you're interested and skip everything else of your table, right? This drastically reduces the amount of I/O that the system has to do from the underlying disk. So let's look at example. So let's say you have that table called as deep dive, right? It has 3 columns, and you're ingesting, let's say, those 4 records into this particular table, right? What you see on the bottom left is basically a representation of the underlying blocks for those columns in the in your table, right? So when you let's say have that kind of a table and you submit a query like select min of date from a deep dive table, if you're storing on a row-based storage, what needs to happen is it needs to read all the rows of all the columns, but the query is interested in only on the date column, right? So while it has to read all the columns, bring that all the data into the memory, and then filter out what is not required and only compute the minimum of the date column, right? So this basically leads to a lot of unnecessary read from the underlying disk, unnecessary IO operations on the underlying storage system. Now, if you're able to flip that model, and if you're able to store in a columnar fashion, right, instead of a row-based fashion, what really happens is when you submit the same query, you're able to read only the date column and compute the min of the date, right? So this basically scans only the relevant blocks from the underlying disk for the particular column, drastically reducing the amount of IO that needs to happen on the system, right? Awesome. So that's columnar, right? The first concept that Redshift employs to reduce the amount of IO, right? The second thing that Redshift can do to reduce the IO is compression, right? So as is fairly evident, so compression allows us to store more data on a given block, right? Which means that on a single IO operation, we could basically read more data from the underlying blocks than compared to, let's say, a not so compressed table, right? Now, typically on a conservative number, you would be easily able to store 2 to 4 times of raw data by leveraging compression within the cluster, right? We will talk about the ingestion mechanism, but we recommend using the copy command to load data into Redshift from S3. When you leverage the copy command, it automatically compresses your data by picking the right compression encodings for your table, right? We'll talk about it in a little bit more detail when we talk about the ingestion mechanisms. So going back to the same table, the deep dive table, what you could do as a customer is that we support about 11 different compression encodings, while the copy command allows you to automatically pick up the right compression encodings. You as a customer, if you know a particular column benefits from a particular compression encodings, you have the option to define a compression encoding for a particular column, right? So in this example, you can go and say the ID column needs to use Z standard, the date column needs to use run length, and so on and so forth. Now, if you're able to couple this with the columnar architecture, what this allows you to do is that each column can potentially occupy different storage space because it's columnar, and each can benefit from its own compression encodings. Now think about this on a row-based storage. If you apply compression, because a block contains multiple columns of a single row, the compression encodings will not work equally for all of the columns, right? It is not effective on a row-based system. But in a columnar system, the compression encodings are very effective because you're storing in columnar format. A particular block only contains values of a particular column, and you're able to get the maximum compression benefits for the particular column, right? So this drastically reduces again the IO operations from the underlying storage system. So the best practice recommendation there is to apply compression to all the tables. If you're starting out fresh, when you have an empty table, when you load using the copy command automatically analyzes, samples the first a few 100,000 records, and then picks up the right compression encodings and applies compression for your table. So that happens automatically when you load data into, let's say, an empty table, right? If you want to figure out whether your tables are compressed or not, if you're unsure, there is a query at the bottom right here. If you run that query, it can tell you basically whether a particular column of your table is compressed or not, right? If it is not, we would highly recommend you to go and compress your data so that it helps us reduce the amount of I/O. So we spoke about columnar, we spoke about compression. Let's talk about the next concept, which is zone maps, right? So zone maps are nothing but in-memory metadata about the underlying blocks in your cluster, right? So remember, each block is holding a particular column's value. So let's say you have a, ID column and a particular block has values of, let's say, 10,000 IDs, right? Now, what the zone map does is that it maintains the min and max value of that ID in that particular block, right? Now, why this helps is that when the leader node is preparing that execution plan, it can refer to zone map and figure out which blocks needs to be read and which block can be skipped. So let's say you have a filter clause on that ID column. You're only interested in, let's say, a particular ID or a particular date. If we know the min and max values, we can figure out which block can be skipped because you have a filter clause for your query, right? That's where zone map helps. So that's one concept. So zone maps is a result, is a behavior on the system that happens automatically, right? Now, but what you can do as a customer to influence a better zone map is to do something called as data sorting, right? Now, what data sorting allows us to do is if you define sorting based on a particular column, we are going to physically sort the data and store the data in a sorted fashion in the underlying blocks and use the sorted mechanism to prune the blocks by leveraging the zone maps, right? So if you have a sorted block, it's perfectly sorted. You exactly know what is the min and the max value. And when you fire a query with a filter, we can clearly figure out, okay, go to this particular block, read only these values from the particular block, right? So sorting helps us to run all those range restricted scans and prune blocks effectively, right? How do you pick up a sort key? It's going to depend on your query patterns, your business use cases, how you define your schema, and so on and so forth, right? So most data warehousing use cases have some kind of a date time column as part of the filter. So it's generally a temporal column which is used as a sort key, and you can pick up that as your sort key for your table, right? So here's an example. Let's go back to the same deep dive table. We have those three columns, right? So this was the original table, right? We had ingested 4 records, right? 2 SFO locations, 2 GFK locations, and a few values for the date column, right? Now, if we go and add a sort key, right? You can add a composite sort key on one or more columns. So let's say we go and add sort key on date and location. Essentially, we go and sort by date and then by location, and then store that in that fashion in the underlying disk physically, right? We are effectively sorting it and storing it as a sorted data set in the underlying disk. Now let's see an impact of this and how zone maps help in optimal partition pruning, right? So let's say we had an unsorted table, right? And these yellow boxes represent the physical blocks of this unsorted table, right? The zone map for this particular unsorted table will have values like min of 1st June and max of 20th June for the first block and so on and so forth, right? So while the first block says min is 1 and max is 20, right? Now let's say I go and fire a query where it says date is equal to, let's say, 6th, right? Now we may have to go and read all those 3 blocks because the first block has min and max as 1 and 20. The third block also has, and fifth block also has, and so on and so forth. Now, it's quite likely that while the first block has 1 and 20, and you had a condition for 6, it may only have values of 1 and 20. 6 may not be present because it is not sorted, right? Now, if I sort it, and the table is perfectly sorted based on the particular, let's say, date column, and if I have the same query, we can go to a particular block and say read only this block and skip all other blocks from the underlying disk, right? This has a direct impact on how much data we have to physically read from the underlying disks, right? So the best practice around sort key is to place a sort key on columns that are frequently filtered, right? On most fact tables, we find a temporal column like a date time column as a natural choice, right? So pick up those and leverage sort keys for all your partition pruning, right? If you have a well-established workload, so let's say you picked up a sort key, it's been under use for, let's say, last 6 to 8 months, a lot of queries have gone through. You could use these utilities. I'll give you a reference towards the end of the deck, but these utilities can figure out what is the right sort keys based on what queries are being fired by the end user, right? So you might have designed the schema based on some initial inputs picking up a particular sort key, but the users could be using a different filter class altogether. So this particular queries will help you figure out what are the optimal sort key recommendations, right? Okay, so that's data sorting. Let's move on to the next concept, which is around slices, right? So if you recollect, the Redshift cluster has one leader node, and we have a bunch of compute nodes. You can decide how many compute nodes you want, right from 1 all the way up to 128, right? Now, a slice can be thought of like a virtual compute node, or let's say the smallest unit of compute resources available within a compute node, right? So each compute node is further bifurcated into what is called as slices, right? The number of slices for a particular compute node is fixed. It's documented, it doesn't change. So it's either 2 or 16 or 32, depending upon the node type, right? So let's say if it's a DC2.large instance type, it has 2 slices and it's documented, right? What that essentially means is that if a node has 2 slices, the total resources available in that node is divided by 2 and is given to each slice, right? So on the DC2.large, it has 2 CPUs, 15 GB of memory, and 160 GB of storage. If you have 2 slices, each slice get an equal portion of that, right? Now, where this has an implication is when you submit a query, each slice is basically going to process only its own data. What this means for us is that if you have a 10 node cluster and each node has 2 slices, you have 20 slices altogether. You want to make sure that all 20 slices are able to utilize and work the same way. You don't have one slice doing more work than the other slice in the cluster, right? You want some kind of a uniform usage across all the slices in your cluster. All right. When you load data into Redshift, we're going to distribute the data and store the data across all the compute nodes, or actually all the slices, right? Slice is the one which is actually holding the data as well. So we're going to distribute the data across all the slices in your cluster. Now, there are a few choices in terms of how data gets distributed, depending upon how you want the system to distribute it. You as a customer have some control over how the distribution happens. It's called as distribution style. And there are 3 options really, right? You can have a key-based distribution, or an all-based distribution, or an even-based distribution. The primary goal with distribution is to make sure that we are able to evenly distribute data across all the slices and evenly process the data when you submit a query. So when you submit the query, you want every slice to do equal amount of work on its own data without doing a lot of chatter between the slices, so that you get like maximum parallel processing. Each slice does its own work, sends back its own results to the leader node. The leader node basically aggregates the result and sends back to the client. So there's nothing in between, no internode communications, no inter-slice communications, no movement of data, and so on and so forth. That's our eventual goal, right? Now let's see how you can use different distribution styles and distribute the data, right? So let's go back to the same table, the deep dive table. We have 3 columns, right? And we have 3 choices, right? In terms of the distribution style. So when you create the table, you're going to say dist style and then nominate one of those styles, even, key, or all. The default distribution style, if you don't mention anything, is even, right? Now let's go back to an example. Let's say we have the table and we define distribution style as even, and we are inserting those 4 records into the table. Now what even does is that it does a round robin distribution of the data, right? So we simply look at the incoming data. We simply distribute that in a round robin fashion from one slice to the next slice and so on and so forth. So those 4 records, if you see, the first record is going to go to the slice 1, the second record there, third record there, fourth record there, right? So each slice basically gets in a round robin fashion. If you load subsequent data, it keeps going on a round robin fashion. So really you don't have any strategy here. It's simple round robin, pure brainless round robin kind of a model, right? Now let's look at the other distribution style, which is a key-based distribution, right? Now this is where you say when you create the table, you want a key-based distribution style, and you actually nominate a particular column on which the distribution needs to happen, right? So in this case, you're saying that it's based on the location column. Now, when you define something like this, we take the same data set. What really happens is the first record goes to the first slice because it's SFO, and the second record goes to the second slice because it's JFK. So what you see here is we are basically hashing the value of that particular column, and for every unique hash, we're basically sending it to a particular slice, right? Now, first went there, second went to the second slice, the third record, because it is again SFO, it goes to the first slice, and the fourth record, which is JFK, goes to the second slice, right? So if you have nominated a particular column, we take the value of the particular column, we hash it, and all the values of a particular hash goes to the same slice in the cluster, right? Now, where this is helpful is that when you are, let's say, performing joins on group bys, each slice can independently work on its own data, right? So if you fire a group by operation, if it's going to group by SFO, that operation can work within slice 0, and for JFK it can happen within slice 1, and there is no need for, let's say, cross slice or cross node communication, right? Now, what you'll also notice in this model is a downside where the other node, which has 2 slices, they don't have any data at all in this example, right? Now, that's basically an anti-pattern where if I pick up a distribution key and it results on uh, a certain number of slices having more data than other slices, then essentially when your query is running, it is not going to utilize equally all the slices in your cluster. So each slice is going to do different work, right? So some slice could be doing more work, some slice could be just sleeping because they don't have any data for the particular query, right? So that's something that you want to avoid. You want to pick up a key which gives you good cardinality and gives you good distribution across all the slices. Now let's say we change the distribution key. Instead of location, we pick up, let's say, ID. What that happens is it again gives a better distribution where different IDs goes to different slices, and if you again get ID is equal to 1 and 2, it will go to the respective slices, right? So obviously I kind of fake this example, but hopefully it gives you an idea in terms of how the disk key based distribution works for you, all right? The last option for you from a distribution style perspective is an all based distribution, where if you define a table with all, as a distribution style, we take a copy of the data and we maintain the entire table's data on the first slice of every node in the cluster, right? So every first slice in every node contains the full copy of the entire table's data set, right? That's why it's called as all-based distribution, right? So those are the three different distribution styles you really get. So when do you choose a key-based distribution? When do you choose an even and all, and so on and so forth, right? So a key-based distribution works really well for large fact tables, right? So if you have large fact tables and you frequently join those fact tables with dimension tables, right? The join performance can be better because if you define if you define the join clause as the distribution key, then data co-location happens, right, between those tables. So because of that, there is no internode communication. The join happens locally within the slice, and the performance is much, much better, right? So similarly, group by operations, join operations, all of them benefit by a key-based distribution, right? And like I said earlier, if you're picking a column, you need to ensure that there is high cardinality so that it doesn't result in skewness, where one slice has more data than other slices in your cluster. So there is a system table called as SVV table info, where if you fire the particular query, there is a column called as skew rows, which can tell you if there is data skewness. What that skew rows really does is that it gives you a ratio between the slice that has most data with the slice that has least data. Ideally, if that number is close to 1, it means that more or less all the slices have equal amount of data. If that number starts going to, let's say, 2 and 3 and so far, it means that you have one slice which is having twice or thrice the data of other slice in the cluster. So there is significant data skewness, right? So that's helpful. An all-based distribution, we really see that coming along for the smaller tables, where if you have, let's say, smaller dimension tables, you can keep a copy of that across each slice in your cluster, right? Now, what we call as a small table in Redshift is typically tables which have less than 3 million rows, or small to medium tables. If you have those dimension tables, you could simply use an all-based distribution, and it keeps basically a copy of the entire table on the first slice in the cluster. Now, an all-based distribution may not be efficient for very large tables, because you would basically pay you basically end up spending a lot of money on just storage, right? Because you're replicating the entire table data across all the slices, right? An even-based distribution style is really helpful. Let's say if you're completely unsure, you do not know where to start with the even-based distribution. It's not so bad. It could be a good start, and once you start running some use cases, if you figure out a pattern, then you can look at changing a distribution style for your table. So the summary from a table design perspective is picking up the right distribution style for your use cases. That's going to be a key driver for getting the best performance from your system. Adding sort keys on frequently filtered columns is going to help you maintain a better zone map, so that we are able to prune the right partitions and read only the blocks that are necessary, right? Do apply compression to all your tables. The copy command on an empty table picks up compression automatically. You can also optimally specify a compression encoding for your table, right? You can also run the command called as analyze compression, which will automatically recommend which is the right or optimal compression encoding for a particular column. The other thing is there is a general behavior where developers, when you define your table, you try to define column lengths with the maximum possible length, right? So let's say if you have a varchar or a char, you just say 65536, right? Because you're unsure what's going to come in. We generally don't recommend that, because what's going to happen is if you define a column which is much bigger than what it's actually going to hold, the memory allocation for the particular column is going to depend on how wide the column is, right? let's say you have defined a column as varchar of 65536. The system is going to allocate when the query is running 65536 of memory for the particular column, right? For every column for every column value of your table. But in reality, it's just a varchar of 256 or whatever it is. So you're going to waste a lot of memory just because you're declaring very, very wide columns, right? So keep it as wide as necessary so that you are able to benefit from better memory utilization. Okay, so that's table design. And let's move on to the next topic, which is around storage, ingestion, and ELT. Okay, so before we jump into ingestion and ELT best practices, some quick note on the underlying storage and how does it really work in the system, right? So when you spin up a cluster, you choose the node type or the instance type. We advertise the storage capacity for the particular instance type, right? So for example, DC2.large has 160 GB of storage, right? So that's the storage that as a customer you get to store data. That's your actual effective storage space that you can use to store your data. And with compression, obviously you can store more data as well. But behind the scenes for that particular compute node, we are throwing up typically 2.5 to 3 times of that advertised storage capacity, right? Why? Because each compute node actually holds its own local data, whatever it's supposed to hold, but it also holds the mirror copy of another compute node. So if you have, let's say, a 3-node cluster, each node is going to hold its own data and also is going to maintain a copy of the other node in the cluster, right? Now this basically allows us for handling things like failures, like for disk failures, node failures, and so on and so forth, where we'll be able to quickly replicate data from other nodes in the cluster, right? That's how it works behind the scenes. So when you have a table, when you load data into the table, a global commit will ensure that all the permanent tables, right, when you are ingesting data, we have returned the data to the local node and also to another node in the cluster. Only then the commit is successful, right? So only if we have successfully returned to the local node and also a copy of the data into the other node, only then the commit goes successful, right? So this ensures that you have redundancy for your data when the commit happens, right? So you basically get redundancy out of the box. What also happens behind the scenes is that while we are redundantly copying the data to the other compute node, we are also asynchronously backing up the data to Amazon S3 as automated snapshots, right? Now, how these snapshots are triggered are either on 5 GB increments of data or 8 hours, whichever happens early. We automatically trigger an automated snapshot and keep a copy of the data in S3. Now, this is useful for, again, handling failures, right? If you have a node failure or an entire cluster level failures, to restore data to your cluster, we would use a combination of what's available on other compute nodes and also what's available in S3 to quickly replicate the data, right? Now, that happens automatically for permanent tables, but there are also a lot of use cases where you would create temporary tables, right? So when you create temporary tables, these tables are actually not mirrored to the remote partition, right? So which means that these temporary tables, the data ingestion is much more faster than permanent tables, right? So we will talk, when you talk a little bit about the ELT aspect, we'll talk about the staging mechanism where you can create temporary staging tables, bring data into that, quickly ingest into those tables, and then move to your production tables. If you have a lot of those temporary tables, and if you also have users creating a lot of scratchpad tables, right? I do a CTAS and create a table, use it as scratchpad, and then I don't need this later. What you could also do is define the table definition with backup no, which means that we will exclude these tables from the backups. So that will help you save on the storage cost, right? Okay, so now that we know a little bit about the underlying storage, let's talk about how to ingest data, right? Uh, so Redshift is a relational database, which means that you could use the leader node to start firing insert queries into it and start loading data into the table, right? But it's not recommended because it's not an OLTP system. It's a data warehouse. It's an OLAP kind of a system. So it's designed for really bulk writes, right? And you want to load data in bulk. Now, what we recommend for data loading into Redshift is to leverage something called as a copy statement, where you can bring your data into S3 and issue the copy statement to load the data into your cluster. Now, when you issue the copy statement, the compute node directly picks up the file from S3 and starts loading the data into the cluster, right? Now, one thing to note here is that if you have a large cluster with many number of compute nodes, you have many number of slices, right? So here's an example where a DC2 has 16 slices on a single compute node. If I have one single file, a slice is going to pick up that file, and only one slice will load that file and distribute the data across the slices, right? So the other 15 slices are going to remain idle because only one slice is basically picking up the file. Now, instead of, let's say, one large file, if somehow you're able to split the input file into multiple files, right? And what happens is each slice can independently pick up one file and start working independently. This will help you ingest much more quickly, right? Because you get parallelism by utilizing all the slices. So our recommendation there really is to have the number of files as a multiplier of the number of slices in your cluster. If you have 16 slices, have number of files is a multiple of 16, right? 16, 32, and so on and so forth, so that each slice can pick up a file and work on it independently. You can also look at an optimal file size. The recommendation there is a file size of between 1 MB and 1 GB. You don't want to go too small. That'll make like more S3 calls. You also don't want to have too big files, right? So our recommendation there is around 1 MB to 1 GB after compression. The copy command supports loading compressed file directly using the copy command into the cluster. So it's really designed for large writes. It's a batch processing system. Try to load data in bulk by bringing the data into S3 and leveraging the copy command, right? Updates and deletes. So underneath, we basically have immutable blocks, which means that when you have, let's say, updates and deletes, we really don't go and delete the data physically from the underlying blocks. We basically only go and logically mark data. So when you go and delete the data, we say simply logically this particular data is deleted. An update is also a delete insert for us, right? So the deletes are essentially logical, which means that you have to do some kind of a maintenance to recover the space and reorganize data, right? And that's where something called as a vacuum operation is required to remove those ghost rows, which are like logically deleted from your table. So let's talk about a practical use case where you have some kind of upserts happening. You have an existing data. So this is again going back to the same deep dive table. I have those 4 records, and I'm getting a new data set which has 2 records which are like an update for an existing record. The same AID 1 and 2, there's an update for that record. And I'm also getting 2 new records which are going to be new records, right? Inserts basically, right? A typical upsert operation. So how do you kind of go about doing this on Redshift? Now, the recommendation there is to think about having a staging table, right? So define a staging table, load all that data into the staging table, delete the duplicates from production table, and simply insert an append from staging to the production. So the way you would do it is, let's say you begin a transaction, you create a temporary table called as a staging table. You can say like the production table. So when you say like production table, we copy the entire table definition from the production table, including the compression encodings, which means that when you run the copy command, you can turn off the compression exercise. You can say comp update off. So the copy command does not do automatic compression, right? It doesn't have to sample and figure out what compression encodings and so on and so forth, because the table already has predefined compression encodings, right? So you trigger the copy command, data gets copied into the temporary table, and then you say delete from production using staging, where ID is equal to ID from production is equal to ID from staging, right? And then you insert from staging into production and drop the staging table and commit, right? So this is the classic UPSERT recommendation from our side. What this will definitely require is to run those vacuum operations later, because you are deleting records here. At some kind of a maintenance interval, you have to run those vacuums to recover those ghost use cases, right? So the best practice from an ELT perspective is leverage a staging table uh, with like a command like production table, so that compression encodings are automatically copied. You can turn off comp update off, so that copy does not perform additional compression activities. Um, and for very large number of rows, let's say if you have a table where you have to load hundreds of millions of records, right? Very large ingestion. What you could do is, you instead of doing insert into select, you could also use a command called as alter table append, where you can have a staging table which has, let's say, hundreds of millions of records. You could say alter table production append staging table. What we really do is, we don't actually do an insert into the production table, but we simply move the blocks around, saying that these are the new blocks the production table points to, right? It's much more efficient. It's not known to a lot of people, but if you have like very large ingestion, alter table append is also useful. I touched upon vacuum and analyze, right? So vacuum is the command that you have to run to globally sort the table again and remove the rows that were marked as deleted. So when you delete the record, we actually do a logical deletion, which means that we have to physically again recover those data. So vacuum will do that. Now, because it's a logical delete, the zone maps also goes for a toss, right? So if you delete and let's say insert a new value for the same data, the new value gets appended at the end of the block. So the zone maps are actually out of date, right? So vacuum will remove all those rows and also globally sort the table again, so that the zone maps are also updated, right? Analyze is another command which also helps in updating the table statistics. If you have done, let's say, lots of upserts and inserts and data loads, the table statistics could be out of date, right? So analyze will also help you to update those table statistics. So our recommendation around vacuum and analyze is run it as necessary, like depending upon how frequently you load data and so on and so forth. So we see most customers doing like a daily vacuum or a weekly vacuum during, let's say, a maintenance window or a off-peak time, right? We also have a utility called as Analyze Vacuum utility on our GitHub repository, which can be used to analyze and vacuum all the tables in your cluster in an automated fashion without you doing this manually for every table. Okay, so hopefully that gave you some kind of idea around data ingestion, some best practices there. Let's move on to the other topic, which is around workload management and query monitoring rules, right? Now, this is another important concept of Redshift, where so you're going to use the cluster. People are going to submit different types of queries. Maybe people are using BI dashboards like your Tableau or Click and so on and so forth, or they simply use a SQL client to fire queries to a cluster, right? Now, when you expose a cluster to many users, naturally, you're going to have different types of workloads running on the cluster. So what I really mean by different types of workloads are, so some could be firing a very simple query that runs for about 5-6 seconds. Some other user could be firing a very long query which scans, let's say, billions of rows. When these things are happening, you could also have some kind of ETL or an ELT pipeline which is loading some data into your cluster, right? So you have all these different things happening in the cluster, and all of them are kind of fighting for resources, right? They are kind of fighting with each other to get maximum resource from the cluster. So how do you manage these different types of workloads is all about workload management. So Through workload management, what you could do is that you could define what's called as queues, right? Now, by default, the cluster has one default queue. When you submit a query, the query goes to the default queue. In addition, you as a customer can define additional queues and assign a percentage of the memory to each queue. If I have, let's say, total 100% memory available in the cluster, you could say 50% goes here, 30 goes here, and 20 goes here for different types of queues. And then when your user submits the query, you can route the queries to a particular queue based on user groups or query groups that you can define, right? Now where is this useful? So let's go with an example, right? So let's say you have three different types of use cases. I have a ingestion, light ingestion that happens, let's say every 30 minutes or every 15 minutes and so on and so forth. You also have the business hour during which your users are utilizing it for peak queries, right? 7 a.m. to 7 p.m. And during the night, you have your heavy ingestion, daily loads where you're loading data in bulk, doing multiple ELTs and ETLs and so on and so forth, right? So different types of use cases used by different types of people in your organization, right? Now, what you could do to make sure that each one gets their own resources, right? I can go and define multiple queues in the system. So there is a default queue which the system comes with, right? It comes with 5 slots, right? So each slot can basically run one query. If it has 5 slots, it can run 5 query, right? Now, in addition, you can create additional queues like ingestion queues and dashboard queues. And you could say for dashboard queue, which is where all your users are using a dashboard to submit queries, I want to give 50% of the memory. That's where my preference is, give more memory there, right? For my ingestion, give 20% of the memory. For my default, which is where everything else goes, give 25% of the memory, right? Now, this way, you are able to kind of give different resources to different queues. And what you're also doing is that you are defining how many slots you want to have in each queue. The total number of slots that you can have is 50, right? That's what the system supports, right? Now, we don't recommend you to go all the way up to 50, right? We recommend you to keep it around 12 to 15. I'll tell you what these slots really mean. These slots are nothing but slots in which your queries can run. If I have 10 slots, I can run 10 queries in parallel, right? So in a way, it kind of defines what the concurrency is, right? But what's also not understood is that the slot divides the memory available in the queue equally. So let's say you go back to the dashboard queue, it has 50% memory, right? Let's say the cluster has 3 nodes and each node has 15 GB memory. So you have 45 GB memory across 3 nodes. So this particular queue takes 50%, which is about 20 to 23 GB memory, right? I have 10 slots. So 10 slots, that 22 GB is divided across 10 slots. Each slot gets 2 GB of memory. That's what this really means, right? So when a query runs in that particular slot, it can take up to 2 GB of memory. Now, what if you go overboard and you say, no, I want more concurrency. Let me go and increase that slot from 10 to 25, right? What it really means is that that 22 GB, instead of 22 GB by 10, it's now 22 GB by 25. So each slot is now getting less than 1 GB of memory. What that means is that if your query needs more memory, it's now not going to have that much amount of memory. It's now starting to going to spill to disk. So a query that could have completely run in the memory will start spilling to disk, thereby causing more damage if you have more number of slots, right? So our recommendation, that's why, is to keep the total number of slots around 15, but effectively define multiple queues and start segregating workloads and send them to different queues. Now, okay, this is okay. You can have different queues. I can send queries to different queues and so on and so forth. But even within the default queue, I have no control over what the user does, right? I don't know what they will submit. Some will submit long running queries, some will submit short queries. Some will write a query and they'll forget to put a limit class. This is a classic problem, right? How do I handle that, right? That's where query monitoring rules come into picture, where you can define rules for your queues to automatically handle these kind of conflicts and runaway queries in your cluster. Now, what you could do is you can start having rules defined which look at specific metrics and start taking action based on those rules, right? So we expose a number of metrics for the query, things like, query execution time, how much CPU was used, how many rows were scanned, and so on and so forth. Very exhaustive, right? And you could say if a query in this particular queue scans more than 1 million records, do something, take some action. That's basically a rule, right? So you could simply say, pick up the metric as number of rows scanned. If it's more than 1 million, take some action, right? What the action can be, or one among the three, simply log it, or abort the query, or hop the query. So logging simply logs the query into a system table where you can come back next day morning and find out what happened. Abort is simply punishing the user. You fired a bad query, I'm going to go and kill you, right? Hopping is, okay, so I have a default queue. That's where everyone is submitting. Somebody sent a bad query. I want to knock you off from this queue and send you to, let's say, a different queue. I have a lesser priority queue, send that person over there, right? So that will help you again manage the workloads in your cluster, right? So the recommendation from WLM and QMR is limit the total number of slots to 15 or less. Define multiple queues depending upon different workloads, different users, and so on and so forth in your cluster. Leverage QMR to start taking actions. The first step could be simply log it, or if you want to even go out and punish people, you can start aborting queries. And you could also start setting timeouts, right? A particular query can only run for this much amount of seconds or this much amount of minutes, right? In addition to all of this, there is also a default super user queue that we create for every cluster. Retain that so that you can use that for any admin activity. So in case things are haphazard and admin has to take some action, you do need that super user queue, right? So do use that for any of your administration activities. Okay, so that's around WLM and QMR for workload management. What we also did was came up with a feature recently called as results at caching. Now, what this really helps is that a lot of times we find these BI dashboards where there are a lot of typical repeated queries, right? People keep sending repeated queries to your cluster. It could be that they're just refreshing the screen, or they went out and came back and they want to see the data again and do something else. So a lot of these repeated queries does get submitted to the cluster, right? And again, they kind of go and hog the resources, right? Now with results at caching, what we really do is we start caching the result of your query. So that if the same query comes back again, we skip everything. We skip WLM, we skip processing, nothing really happens. We simply return the data from the cache, right? So this is maintained in the leader node's memory as a cache, so that when you're getting let's say if the query runs for the first time, it doesn't find anything in the cache, it actually goes and physically runs on the cluster. The result set gets cached in the leader node, and the result gets sent back to the BI client. Next time the same query comes, no processing, no WLM, nothing, simply return the result from leader node, right? So this helps in again optimizing the workloads because there's lesser number of work being done for repeated queries, right? So results at caching is turned on by default now, so you should start seeing benefits in your cluster, right? So the next thing that we did is something called as short query acceleration. This is again in the WLM space to help you optimize throughput from your system, right? Now, the other common concern that we heard from your customers is that when different types of workloads start running on the cluster, what we are not able to avoid is there could be a small, simple query, a query that runs for 3-4 seconds, right? But because of the WLM settings, what's happening is my long running queries are blocking my short queries. They are currently running. I have no free slots for my short query to run. So it has to go and wait in the queue, right? So typically the long running queries start kind of blocking the short queries and they don't find enough space to run, right? But these short queries, given a chance, they can actually quickly run and get out of the way, right? So what SQA really does, SQA is short for short query acceleration. We deployed a machine learning model in your cluster. It's a simple classifier model where it uses machine learning to start classifying your queries into short and long, right? It basically becomes better over a period of time. It starts learning as you submit more and more different types of queries into the cluster, and it starts classifying, okay, here's a new query. I find it to be a short query. Now, if it finds a short query, it momentarily pauses one of the existing long running queries, gives the short query to run, gives a chance for the short query to run, and then the short query finishes, and then the long query starts running again, right? So this way, your short query kind of gets an express lane where they're kind of bypassing all the queues and the WLMs and quickly run and get out of the way, right? Now, the impact of this is that the long running queries could take slightly longer to run, right? So let's say the query was running for 28 minutes. It could run for 28 minutes and 30 seconds because it got paused in between and so on and so forth, right? Because the short query has to run, which is probably okay because it's a long running query anyway. Somebody fired it, went for a coffee. They're gonna probably get the result in another 30 seconds or so. This is probably okay. But if you see from the overall system perspective, the total number of queries that you're able to run in an hour increases significantly because these short queries are now running much quickly from an end user perspective. So you get more throughput from the system, right? Now this is also now enabled by default for new clusters. You can run a command, it's there in documentation, to find out whether SQA is enabled in your cluster or not, right? If it's not enabled, we would highly recommend you to go and enable it for your cluster. Okay, so I think we spoke quite a bit about WLM, QMR, short query acceleration, results and so on and so forth. All of them kind of help you manage the workloads in your cluster so that you're able to give optimal resources for the right kind of workloads within your cluster. So let's talk a little bit about the node types and the cluster sizing. So as I said earlier, we offer different types of nodes, primarily classified as dense compute and dense storage. Dense computes are nothing but nodes with solid state disk. So they have SSDs on them. They come with better performance than the dense storage. Dense storage are magnetic disk. So they are really meant for very, very large deployments where if you have, let's say, hundreds of terabytes or petabytes of deployments, you need like much more larger storage footprint. That's where dense storage comes into picture. You do get two different types of instance types within them. DC2 has large and 8XL. DS2 has X large and 8X large, right? Each with varying configurations on CPU, memory, and storage. From a cluster sizing perspective, our recommendation there is if you're running it in production, we recommend minimum 2 compute nodes so that you get high availability and redundancy for your data. The leader node is automatically given to you at no additional cost. We will also recommend you to maintain 20% free space on your cluster. So why do we recommend this? Is primarily because we need free space in the system for things like scratchpad, logs. If you're running vacuum, we need storage space to basically resort the table. Temporary tables will use space for intermediate results and so on and so forth, right? So do leave out 20% free space in your cluster. So which means that 60 to 70% is what you should look at in terms of overall cluster space utilization. The moment you're hitting at 50, 60, you should start thinking about adding more storage to your cluster, right? If you are currently on DC1, which was a previous generation dense compute, we highly recommend you to move to DC2. DC2 is significantly faster than DC1, and it comes as the same price as DC1. So there is no additional cost for you, and you get better performance from DC2, right? So that's about Redshift. And I also mentioned that Redshift can help you extend your data lake, data warehouse to data lake, right? You can use Spectrum to start querying data available in S3, right? So what Redshift Spectrum allows you to really do is from your Redshift cluster itself, I can now start firing queries which can directly run against S3's data. I can store some data on my S3 bucket and the query can directly run against that data. You could also go one step ahead and say, I want to join data between what is available within Redshift and what's available on S3, right? The best part of Spectrum is that it's an infrastructure that you do not manage. So we basically have a warm pool of infrastructure that we are managing on your behalf, and you pay only when you utilize that infrastructure. It's a pay per query kind of a model. Unlike in Redshift, where you are having a cluster, you're going to pay by the hour for your nodes. In Spectrum, it's a pay per query model. If you fire a query, if the query scans fire a terabyte of data, you pay $5, right? And we support open file formats like Parquet, ORC, Avro, CSV, and so on and so forth, right? Now here's how it works, right? So you have your SQL client, you have your Redshift cluster, which is the blue portion. You also have the Spectrum layer, the green portion, which is really not visible to you. But what you could do is you could create an external table that points to the S3 data set. And when you fire a query against that data set, it actually leverages the Spectrum layer and runs that query against your S3 data set, right? Now, what this model allows you to do is even have multiple Redshift clusters leveraging the Spectrum layer and accessing the same data set that is available on S3. So this allows you to scale much more than what you could achieve through just one single cluster, right? So all those different clusters can go to a common Spectrum layer and go to the same S3 data set without you ingesting data into multiple clusters. And the best part is AWS Glue gives you a centralized catalog which can be leveraged across all those different clusters, right? So few things from Spectrum perspective, right? So Spectrum, like I said, is a pay per query model. So you pay based on how much data your query scans. If I scan a terabyte, I pay $5. If I scan 100 GB, I pay 1/10 of that, which is 50 cents, right? So the more you scan, the more you pay. The less you scan, the lesser you pay, no brainer, right? Now, again, if you are leveraging columnar formats, it will help you to scan lesser, right? Because again, you're going to run analytical queries against this data set, right? And columnar formats, unlike text formats, allow you to selectively read data. If I am able to, let's say, store data in Parquet or ORC and those columnar formats, when I fire a columnar query, it reads only the particular data from S3, which means that we are able to scan lesser and we will charge you much lesser, right? So here's an example where I had a 1.15 terabyte data set on S3, a text data set. A query was run against this. It took 200 seconds to run. It scanned the entire data set. It cost you $5, right? The same data set, if you're able to convert into Parquet, the data set becomes much smaller because Parquet as a format comes with compression, right? It becomes much lesser, 130 GB. The same query, first thing is it runs much faster because it's able to scan and read only the specific columns. And more importantly, the data scanned is much lesser. It's only 2.5 GB, which means that you end up paying much lesser than what you paid for the text-based format, right? So when you're leveraging Spectrum, always think about keeping your data in columnar formats in S3. The other thing from Spectrum perspective is data partitioning. So for those of you who are coming from Hadoop kind of a background, you know what partitioning means, right? So you are able to now separate the data files based on columns. And if you are having queries which only look at certain portion of the data, you have a filter clause. Through partitioning, we can only read a subset of the files, that again reducing the amount of data that we scan, right? So here is an example. I go and create an external table called as sales event. I have few columns on the table. What I can say is partition by a particular column in the table called as, let's say, month and event, right? And I say location is the particular S3 bucket. Now in that S3 bucket, what I can do is I can create subfolders like sales month is equal to 18-1 / event is equal to 101. I can keep creating these kind of folders and putting data within the folders. And when I have a partitioned table, that particular sales month points to the sales month folder, and event partition for points to the events folder. Now, what is the effect of this? So when I fire a query on a non-partition table, again, it's going to scan the entire data set, right? The first example there, right? Where it scans 74 GB of data, and it costs you 36 cents there. The same query on the right hand side on a partition table, because there is a where clause where ship date is equal to 96, right? So on a partition table, because of the where clause, I can go to the specific S3 folder with the folder's name could be ship date is equal to 1996 hyphen so on and so forth, and read only that, thereby reduce the amount of data being scanned. Significant performance difference, significant cost savings, right? So think about that. So when you're leveraging Spectrum, think about columnar formats, compression, think about having partition data set on S3. All of them will help you reduce the amount of data that you scan and also improve the performance, right? Now, beyond all of that, these are the recommendations that you could think about within Redshift and leveraging Spectrum, right? Now, what we also recommend customers is to start thinking about various analytics services that can be used to run different types of workloads. So while you might have started with Redshift and you're trying to optimize what's possible within Redshift, do not forget that there are other options available within AWS, things like EMR for Hadoop-based workloads. You could start, for example, running Presto-based queries on EMR, or Athena, which is again a pay-per-query model, completely serverless, right? And the beauty of all these services is that all of them can directly interact with S3 as the underlying storage. Spectrum, EMR, and Athena, all of them have direct capability of reading data from S3. And all of them can leverage a centralized data catalog. So your Glue data catalog can maintain the table information, table definitions, column information, partition information, so on and so forth in one place. And you could even use multiple query engines to start processing the same data set, right? So this is taking one step further. So what we discussed so far is what are the best practices, what's possible to optimize your current Redshift workload using Redshift and Spectrum. But beyond that, always there are other options available within the AWS ecosystem, and you could use a combination of these different services to do different types of use cases, right? If you have a developer who would like to leverage Presto or Spark to process the data, you could send them to EMR, right? If you have a lot of current ad hoc workloads being run on Redshift, maybe you can start thinking about moving those workloads to Athena, right? So that helps you again distribute the workload to different services and make sure everyone gets better experience from different services, right? So that's all I wanted to cover, but I would leave with a few more resources that you can probably read later. There are a bunch of utilities available in our GitHub repository. So our AWS Labs GitHub repository has utilities for Redshift. There are better monitoring utilities and UDF functions and so on and so forth. So these are things like admin scripts that you can run for getting more diagnostic information from your cluster. Things like your analyze vacuum utility that I spoke about. All of them are available in that GitHub repository. Do take a look at the GitHub repository. It's very, very useful. If you're not following the AWS Big Data blog, I highly recommend that you follow the Big Data blog. We specifically write about a lot of architecture patterns and also some of these best practices there, right? So from a Redshift perspective, you could look up the Redshift Engineering's advanced table design playbook. It was written by one of the Redshift engineers. He talks about a lot of these best practice recommendations, and also a couple of blogs around Redshift and Spectrum for top 10 best practices in performance tuning, right? So do look at those blogs. It'll give you some more insights into what you could do in your Redshift cluster. That's all I had. Hopefully this was useful. If you do have any further questions, there will be a survey right after this webinar. You can use a survey to send in your questions. We will get back to you with our answers. If you do need, let's say, help from us where you need to speak to someone, some solution architect for your queries, do mention that in the survey. We will be happy to have a conversation with you. So that's all I had. Hopefully it's useful, and you guys have a great evening. Thank you.